All right, so here's a quick question then. Let's find the expected value of this game. Just sort of a quick review. You pay $2, roll a 6-sided die. You win $5. Well, I should say that. Hang on. You get paid $5 if you roll 1 or a 6. Here's just a quick question. Let's see how you guys do. This is a similar question to what I've asked on the exam. It's something along these lines for what I expect you to be able to do when it comes to calculating expected value.
We're doing the graph thing like 0, 1 to 6, and then you do the minus $2, and then
So I would expect you to create some sort of a frequency distribution or a probability distribution on this.
how do we do where, so it's only, you only pay $2 literally 3 times, or $2 per time?
$2 per time. So yeah, you don't get to roll the die as many times as you want. Then I would assume you'd always win. I guess the first question is, does this question make sense? Yeah? Well, just do it for, find the expected value. So what's
1/3?
1/3 of what?
$1.
1/3 of a dollar? I haven't done it yet. So what can you roll on a 6-sided die? 1, 2, 3. You were thinking how many heads do I flip? 5 and 6. What's the probability that I roll a 1 on a 6-sided die? 1/6 or 1/6. What's the probability that I roll a 2?
1.
Okay, good. I assume I don't need to ask the rest of them. Now, when you have outcomes, you need to include that in the table. So what is the outcome if you roll a 1?
3.
3. Why is it $3? Because you paid 2 to play, but you got paid 5 coming back, so your outcome is you win basically $3, right? What's the outcome if you roll a 2? Lose $2, so make sure it's a negative $2, right? And then 3, 4, and 5, same thing. And 6, Same as what? You win $3. Now, how do I find the expected value? So the expected value of this game
Is not 1/3 that way.
well, it was close, right? So 1/6 times 3 plus 1/6 times -2 plus 1/6 times -2 plus etc. down the line, right? Do it for each number. Do I have enough of those? One more. I need one more 1/6. That's a 3, I swear. We're close, right? Not positive.
I'll play no.
Right, so 3 times 1/6, that's a half, right? 1/2 plus a -1/3 plus a -1/3 plus a -1/3 plus a -1/3 plus a half. What's a half plus a half?
A whole.
A whole. What is -1/3 plus -1/3 plus -1/3? A negative whole.
Exactly.
What are we left with? So basically the expected value of this game is that you're going to lose 33 cents every time you play. All right? On average, you will lose 33 cents per time you play the game.
Casino always gets me.
The house always wins, folks. That's how it works. If you played this game infinitely, however much money you had, the house would have it. Eventually. All right, so not bad. So the idea behind this is that this is often the expected value. Note that it's often called this. It's the average. It actually is the mean of a certain probability distribution, okay? So if anybody ever talks about what's the mean of a probability distribution or a probability event, the idea is that you would be calculating the expected value in order to figure that out. Right? And again, it's just a matter of figuring out what's the odds of the event that's going on that you're playing, whatever it may be. Okay? So let's see. I don't want to talk about that. All right, so how about we try doing one of the book problems? Which ones did I assign from that section so that I do one I didn't do, I didn't assign? 4, 8, 12, and 16? All right. 4, 8, 12, and 16. All right. All right, so let's do number 15. Kind of like that one. So, a church is having a $50 raffle. They sell 100 tickets. What is the expected value of buying one ticket for $1? So in other words, you're just going to go, so it's a church charity thing, right? So they're saying, hey, you might have a chance of winning $50. All it does is cost you $1 to buy a ticket. So part of it you may be saying, okay, fine, I'll give you $1 because it's a donation, right? But in theory, it would be nice if you won because someone has to win the lottery. So why can't it be you? And they're only selling 100 tickets, okay? So I think you have a relatively decent shot to win. So it's not a 50-50 raffle, but this one's a,
tickets and you win $500, or $50,
yeah,
so it's 50-50, they get 50.
right. That's the
Not a lot
idea.
of person.
Yeah, I mean that's the idea. Is that the church needs to keep $50 for its coffers, and it'll give $50 of it away to whoever wins. All right, but what are the probabilities and the events that may occur from this game, if you will? So, what are the two events that could happen from this lottery? You win or you lose, okay? What's the probability that you win if you buy one ticket for $1? What's the, oops, put it in the wrong spot, sorry. You win 1 out of 100 times. Now, technically, what's the outcome? 49. Good. Why is it 49 and not 50? You had to pay $1 to get the ticket, and you win 50, not 50 coming back. So you really win $49, right? What's the probability that you lose? Yeah, 99 out of 100. And what's the outcome when you lose? Negative $1. Good. So what's the expected value of this?
You lose 50 cents.
Uh-huh. 1/100 times 49 plus 99 100ths times -1. Well, what's 49 over 100 minus 99 over 100? -50 over 100, or you're going to lose 50 cents. Which is, for a charitable event, okay, no biggie. All right, now the problem goes on and it says, wait a second, you could also buy 3 tickets for $2.50. What is the expected value if you buy 3 tickets for $2.50? So again, the general practice on each one of these folks is create your probability distribution, right? So if you buy 3 tickets for $2.50, what's the probability that you win? 3 out of 100. And what's the outcome? How much do you win if you win?
Oh, I think.
Whatever's 50 minus 250.
47.
$47.50, right? Because this time you had to spend $2.50 to win the $50, so you only win $47.50. What about the lose option?
97 out of 100.
Yeah, 97 out of 100. They always have to add up to 1. And there you lose the 250. So expected value here. We out 100 times 47.50 plus 97 out of 100 times negative 250. Ugh. That's yucky. What's 3 times 47.5? 142.50. Alright. -1, that sounds about right to me. That's what you guys got? Okay, excellent. So the expected value when you buy 3 tickets for $2.50 is you lose $1. How about the last one? What happens if you can buy 5 tickets for $4? Now that you've sort of seen the pattern, right? What are we going to do? What's the probability that we win, folks? What's the probability that we lose? What's the outcome in either one of these? You win $46 if you get one of the lucky tickets, and if you lose $4 because you had to spend $4 for 5 tickets. Now that you got the pattern, 5/100 times 46 plus 95/100 times -4. 2.
1.5.
Should be like 150, right? Why is that? Why is our expected value going up? every time. Yeah, but notice, how much are we paying per ticket? I mean, how much do I pay per ticket when I buy 5 tickets for $4? I'm paying less per ticket than if I buy 1 ticket, right? Why is that?
The world works mysteriously.
I mean, it makes sense if you look at what you get for buying all of the tickets.
Right. Makes sense if you look for at how much you spend for buying all of the tickets. The idea here, folks, is that by selling you tickets for less per ticket to make you buy more of them, you actually lose more money on average in the process. Because you're taking more chances in a game where you're expected to lose. If you're expecting to lose, the more times that you play, the more times you're going to lose. So even though you're paying less per ticket in each one of those events, right? Each time the price of each ticket was less from one to the next. But the expected outcome from us was going to be worse. And that's simply because they're forcing us to play more often. And when the odds are stacked against you, it's always the house's advantage if you play more. And so they want to. And this is exactly why they do this for these types of things, right? Try and get you to spend, because otherwise, right, if you think about it in the first ticket, if you play the first one, the likelihood of you winning is very small. How much did you spend? $1. So you just lost $1, big whoop, right? What's your chances of winning in the second game? Is still pretty close to nothing, but now you spent 250% times what you spent before. You spent 2.5 times, right? You gave them more money. So, thank you. Please come and play again. Sad, but true. Alright? So this is kind of how expected value works and why it sort of gives you an understanding of why the house always wins, right? The more you play, the more you pay, even if they give you a discount on how many times you can play with this fixed amount of money. All they want is the money on the table. That's all they care about. If they can get more out there, and the odds are always in their favor, who cares? This is why when you go to Vegas, folks, you get free drinks, and they give you, entertainment as you're sitting around, because what does it force you to do?
Stay longer.
Stay longer, play more. That's all they care about. Because in the end, as long as you have played enough, you will have lost your money. That's the way it works. Vegas is king, baby. Alright, so anyways, there is expected value for you. This is a great example just to sort of get an idea and a feel for it on top of what we already did. Alright, so that's 5.1. Alright, now into the interesting thing. Yeah, that was pretty much the end of 5.1. Alright, so 5.2 talks about binomial distributions. So binomial distributions, what these are multiple hit or miss experiments, and the probabilities that may occur. So the book talks about a certain amount. The book likes to talk about discrete probability distributions when it talks about this. I like to call it the hit or miss experiments, okay? So the idea behind this is something along the lines of, I flip a coin, say 25 times. What is the probability So this is a probability, calculation that we could do if we wanted to spend time figuring out how many different ways you can flip a coin 25 times. That's a lot. How many different ways can you flip a coin 25 times, and how many different outcomes can you get? Well, when you flip a coin once, you can get 2. When you flip it twice, you can get 4. When you flip it 3 times, you can get 8. When you flip it 4 times, you can get 16.
Is
What
it
if-
625?
Well, it's much, much bigger than that. So 4 of them gets us 16. 5 of them gets us 32. What am I doing every time?
Oh, yeah.
Multiplying by 2. So if there's 25 times I'm flipping it, what do I have to do? You were on the right track, except flip the numbers, not 25 squared, but what does your calculator spit at you back when you put in 2 raised to the 25th power?
Holy.
Wait. What'd you get?
Yeah,
33, 3, 5, 5, 4, 4, 3,
3355
2. 4, 4, 3,
44332.
No,
No,
just
just
3,
3, 2.
Just 32.
It seemed like it was going with that.
Lots of different outcomes, folks, right? In theory, this would be the denominator of our probability distribution, right? Because this is the total number of outcomes for flipping a coin 25 times. It's very, very, very big, okay? We don't want to have to do that. We want to figure out an easier way to calculate this, okay? And that's what the binomial probability distribution is for, okay? So, binomial calculation simplifies this for us. So you should, so somewhere in your book, or actually what you can use if you want, I don't know if you guys have seen this, but you should have had a cardboard piece of paper in your book somewhere. Yeah, if you unfold that thing, what that thing contains are all of the formulas that you use in this class, subdivided into each chapter.
Do we get to use this on the test?
Of course you get to use it on the test.
Score.
I would not expect you to memorize these sorts of formulas, folks, that's ridiculous. But at the same time, you have to know when to use them and how to use them, right? So if you look at the binomial distribution calculation, what does it say for the probability that x equals x? It says it's this weird thing, p to the x times 1 minus p to the n minus x. And now what do all of those letters mean? First off, what does the NCX mean?
Combinations.
This is the combination of n things taken x in time. This is what we learned back in chapter 4. Alright, so we'll play around with those a little bit more, and that's why we covered those in chapter 4, because we used them here in chapter 5 on a regular basis. Okay? So n in this formula is the total trials that you're going to take. So in this case, how many times are we flipping the coin? 25 times. X X is the event, little x is the number of correct occurrences that you're looking for in the event. So x is flipping a coin 25 times, little x is hitting the heads 10 times on those 25. Generally speaking, x is the event. And so when you say event equals something, is that the event is having a specific thing occur inside of it.
So a total success is the little x.
Yep. Total success is the little x, and P is the probability of success. So for my example that I just did right there, what is n for my example? 25. What is little x? 10 heads. And what is p? What is my probability of success? What's the probability that you flip a heads? 1 out of 2. Or 1 half. So it's just the probability of it happening in one event. Right? When it happens in one event, what's the probability that it does occur? Alright? So now, use this inside of that formula, and it will calculate the probability for you. Okay? So basically, if you calculate combination of 25 things taken 10 at a time, and multiply by 1/2 raised to the 10th power, and then times 1 minus 1/2 raised to the 25 minus 10th power. And what is 1 minus 1/2, folks? It's just a half. So really those two things are the same.
So what, oh, I didn't see that. I was gonna ask what the 25 to 10 was, but I didn't see that.
Yeah. It's part of the formula, if you will. So this is obviously a calculator problem, folks. First off, how are you going to calculate the combination of 25 things taken to 10 at a time? Put it in the calculator. 25, hit that PRV, you're hitting the CN, NCR, 10. So you get this awesome number, 3268760. You use the PRV button for
No, but
you see it?
yeah, I got the same number.
Okay.
I think I know how to use it.
You're going to multiply that by 0.5 raised to the 10th power. And you're going to multiply that by 0.5 raised to the 15th power. So this is how you raise something to a power on these standard calculators, is this little up caret button. Again, if you're using a Casio, you have to use the X to the Y button or the Y to the X button, depending on whichever one you have. When I crank all of this out on my calculator, I get 0.097416639. At least those are all the numbers that I get on my calculator. And so, essentially, the probability of flipping a coin 25 times and getting exactly 10 heads is somewhere between 9.7% of the time, roughly, right? That's it. Yep.
You don't do anything with the exponent of 25 minus 10.
Yeah, what is 25 minus 10?
Oh, the 15.
That's
Okay,
the 15.
gotcha.
Yeah.
I was wondering where that went.
I mean, do the things you can do in your head, So like the 1 minus a half, that's why I said, don't punch in 1 minus a half, type in a half, because you know 1 minus a half is a half, right? So run with those when you get the chance, right?
So, how, like, for that decimal point, how far do you want us to go? I don't want us to go calculator, like.
Usually what I would tell students is that you should round to the hundredths of a percent, right? So move the decimal over 2 to make it a percent, and then round to 2 decimal places in your percent. You can go further if you want. I mean, it's not, this is one of those where it really depends on how accurate you want to be. Because the number is valid to as many places as the calculators can show you, it's just how much you want. So in this one, it'll be really me telling you, round to 4 decimal places, or give me to the 10th of a percent, or something like that. And you guys just have to make sure you follow my directions. All right? Not bad. All right, so should we try something with a slight variation on the theme? All right. So, I roll a 4-sided die, four-sided dice. Let's say 12 times. What is the probability I roll exactly 2 4s? So one of the things that you have to be able to do when you are reading problems like this is tell when it is a binomial problem, as opposed to one of the other ones that we will be doing in a little bit, right? So these sorts of things, hit and miss, you have to be able to see that there is a probability that something happens and a probability that something does not happen. It has to be only 2 real outcomes in here, and sometimes that's a little tricky, right? Because I'm rolling a 4-sided die. How many outcomes are there? 4. How can this be a hit or miss when there are 4 different options?
Because 3 of them are misses.
Because 3 of them are misses, and only 1 of them is a hit, right? 1 out of 4 times, I'm going to roll a 4. If I don't roll a 4, that means I roll a 1, 2, or 3, that's a miss. But you can tell me what's the probability of rolling a 1, a 2, or a 3. Okay? So hence, a hit and a miss. All right? So this is binomial. First off, what's my combinations we're going to work with? 12 is the n. Uh-huh.
Is it the 4 that we're gonna put as the C? I'm guessing it's the 2.
Good call. It is the 2. X is 2 in here because it's the number of successes. I want 2 4s. Okay, so remember X is successes. The only other piece you need is the P. That's where you get the 1 out of 4 from, right? And therefore a miss is technically 3 out of 4, and you get that when you do the 1 minus P. All right? Because here, this is 1/4 raised to the 2nd power times 1 minus 1/4 raised to the 12 minus 10th power.
Why is it?
12 minus 2. Sorry. The other 10, 2. I was doing the subtraction in my head. And again, simplify the stuff that you can do in your head so that you don't have to try and force the calculator to do it for you, right? You know that 1 minus 1/4 is 3/4, and you know 12 minus 2 is 10. That's what I was getting to. 2, 3, 2, 2, 9, 3, 2, 4, 8.
Yeah, we just did, make it a percentage.
Make it a percentage. 23.23%. Not bad odds if you think about it, right? Why did it work out that way?
It's like a quarter of the time.
If you roll a 12-sided die, or a 4-sided die 12 times, how many 4s do you expect to roll? 3, right? Because 1/4 of the time you will roll a 4, and so 1/4 times 12, you expect to be around 3. So the fact that you're only getting 2 of them, that should be relatively common-ish. It's not 50-50, but it is, 3-1, 25% of the time. It's not that unlikely of an event, right? Alright. Note how it works, folks. I mean, the cool thing about this is that when you're dealing with combinations, if you remember when we were talking about it back in chapter 4, I said that it has to do with events where order doesn't matter, right? So when you're dealing with combinations, the order doesn't matter. When you're counting up total number of hits and misses, does it matter when you hit and when you don't hit? No, it's just the total number that you're getting. That's why we're dealing with combinations. And the 1/4 squared, that's just basically the probability of rolling 2 4s. And the 3/4 to the 10th power is rolling a non-4 10 times. That's its probability, right? So built into that is really all of our probability calculations that we were working back in chapter 4 anyways. It's just tied into a formula that seems like it's only specific to binomial, but it's really applicable to any sort of a calculation dealing with probability. So, all right, not too bad though. Again, it's one of those where once you sort of see how to get n, how to get x, and how to get p, it's not too hard. So, let's see if I can give you a book problem that makes equal sense. Oh, sorry. I gotta do one more thing before I go. Yeah, So, let's suppose I flip a coin 8 times. What is the probability I flip less than 3 heads? So when I was asking for exactly, you guys have a way of doing it. But now I'm not asking for exactly, I'm asking for less than. What numbers are less than 3? When you're given a problem that deals with less than or more than or greater than or equal to or less than or equal to, you are going to have to do combinations of these calculations, okay? So you need to calculate the probability that you flip no heads, the probability that you flip 1 head, plus the probability that you flip 2 heads. Because 0, 1, or 2 are all less than 3, all right? Now, the cool thing about flipping a coin, folks, is that this is at least not as bad a calculation as you think. Now, we can go through it the long way, but I want to show you that if you look at some of these problems, sometimes you can make them easier by looking first, all right? So how do we figure out the probability that we flip 0 heads out of 8 times flipping a coin. In theory, let's use the binomial distribution first. What's my n for this event? 8. What's my x? 0, right? I want 0 successful outcomes, right? Raised to the 0th power times 1/2. And what's 8 minus 0, folks? 8. Now let's do the next one. How does this problem change? Take your zeros and make them ones, and then just be careful with the 8, right? Combination of 7 things taken one at a time, times 1/2 to the first power, times 1/2 to the 7th power, right? N is now 1, N is now 8, X is now 1, so 8 minus 1 gives us the 7, and then one more time down the 8, sorry about that. Well, that's 7. It's not 7 choose 1, it's 8 choose 1. And then one more time, the combination of 8 things taken 2 at a time, 1/2 squared times 1/2 to the 6th. That's a quick application of the formula 3 times. And this is where looking at it mathematically can make things a little bit easier. Because folks, what do you notice about these exponents? What's the base? It's always 1/2, right? So the cool thing about this is that this is the combination of 8 things taken 0 at a time times 1/2 to the 8th power plus the combination of 8 things taken one at a time times 1/2 to the 8th power. If I have 1/2 to the first times 1/2 to the 7th, since the bases are the same, you can just add the exponents, right? And you can do the same thing with the 2 and the 6. And so now you can actually start applying some algebra to this stuff, okay? Because now think of 1/2 to the 8th power as being x. You've got a number times x plus a number times x plus a number times x. All you have to do is add those numbers up and then multiply them by x once. So first off, what's the combination of 8 things taken 1 at a time or 0 at a time? By definition, that's always 1, folks. Combination of 8 things taken 1 at a time. And then the combination of 8 things taken 2 at a time. 16, 28. 8 times 7 divided by 2 times 1. And so what you can do right here is realize that these numbers are all multiplying 1/2 to the 8th power. Yeah, you can just add the 1, the 8, and the 28, and just say it's 37 times 1/2 to the 8th power. That's very common when dealing with binomial distributions, because you're always multiplying by the same p and 1 minus p, and so those things can combine to make the problem a little bit easier. Especially when it's a half, because then everything is the same. Right? So you can just quick like crank it out, right? 37 times 0.5 raised to the 8th power. Again, it's perfectly okay if you calculate what each one of those numbers is out and then add them. You're going to get the same answer. And you should have you got the same number, right? Yeah, I mean, that's the nice part about it. But if you can see some algebra tricks to use on these sorts of things, you should take advantage of it when possible, because it does make your lives a little bit easier. All right? I like them, so they're fun. And the cool part about it is that the formulas, I mean, they're not too bad, right? This combination and things take an extra time, not too bad. Now, unfortunately, I could be cruel to you. What is the probability I flip 9 or less heads on 25 flips of a coin?
Just no.
In theory, you know how to do this now, right?
In theory.
It's just annoying to have to do it, all right? And so the reason why I like to point this problem out is that you are more than welcome to use Excel to calculate these values. And what you'll discover when you fire up an Excel spreadsheet is that it actually has some functions that are dedicated to calculating these sorts of probabilities. All right? So, what I'm going to show you really fast here, or hopefully really fast, is the ability to do this quickly using Excel, right? So when you're working in Excel, in order to get functions or to get to the function tables, you have to start by typing in an equal sign. Well, I'm already, hang on. Total zoom in there. All right, so you start by typing in equals, or you can, if you want, go to the function button right up here. Note that there is a statistical set of functions that exist for calculating standard statistical formula that you might want to calculate. Binomial distribution. So now which one do we want to make? There's a bunch of them. We have to be careful, make sure we return with the right one. Ah, yes, just straight binomial distribution, folks. And now all you have to do is figure out in Excel which of the things are n, which of the things are x, and which of the things are p. Same sort of concept, though, right? They'll use slightly different letters. Number underscore s, that's the number of successes. That's our x. So for the problem we were working on, we wanted to have 9 or less, okay? So our number of successes is 9. The trials we're taking are 25. The probability that any one of them is a success is 0.5. And note that there's this last little thing down here, cumulative, on the bottom. Cumulative is how you tell it to add everything down to 0. So if you make this value true, 0.5, because it's 50-50 shot of flipping a heads or tails, right? When you set the cumulative to true, that just tells it to add everything up down to 0 from the number you entered in. If you enter in false, then it will calculate the probability of exactly getting whatever that number that you typed in for successes is. All right? So if you said false, you would just get the probability of getting exactly 9 flips. With true, you get the probability of 9 plus 8 plus 7 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1 plus 0. And it will do all of it for you. All right? And these are the sorts of things that you should play around with so that you can figure out probabilities without having to spend a huge amount of time calculating lots of nasty probabilities and having to add them all up. Right? That would have been 10 long, nasty numbers you'd have had to add together. This does it for you in one fell swoop. I have no problem with you guys sitting down and doing all of the adding yourself if you would like to, right? I got no problems. Right? Because technically you can do this problem by simply saying probability that x equals 9 plus the probability that x equals 8 plus the probability that x equals 7 plus dot 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 plus the probability that x equals 0. There's nothing wrong with doing that. It's a perfectly legitimate technique. It's just going to be painful. Right? It wouldn't be overly painful in here because we can use some of our knowledge of dealing with exponents to make it a little bit easier. But it's still, it's still going to be, sort of a little bit clunky. Whereas if you pop over to Excel and get it calculated quickly, you can see that the probability is going to be somewhere around 11.48%. The true. That's just to tell it to add everything from where I am all the way down to the bottom. Yeah, just type the word in true. Yep.
So, are we gonna have like examples like this on the test though? That are gonna be 9 to 0, and if we can't use Excel on that, so we're gonna have to.
Why wouldn't you be able to use Excel? No.
Oh, it is a table?
Yeah.
Oh, okay, I was gonna say, but do we have to print out our work? That would show you? For
No, I mean,
credit,
if your
or no?
number is right, I agree. So maybe you should show me what you put in so that I can say, oops, what you did was slightly wrong, right?
Well, yeah, but how do you show it on that?
Right here.
Well, how do you like?
Print screen. Yeah. Just say it.
File and email it to him.
You can copy and paste. It's
I don't know, I don't
a word
use
process.
Excel.
Well, you're going to learn a little bit, okay? Or you can do it longhand. I mean, there's nothing wrong with doing it longhand. I mean,
I didn't know.
so you don't have to do this, right? That's the cool part about it, right? You can add. It's okay.
Are you gonna need like put like 20 and 0 on some of them?
No, but I would definitely have to ask you to add 5 or 6 of those. Yeah.
I feel like with Excel, you get less there.
You do have to know how to enter things in. That's part of the problem, is knowing how to use it. I mean, here's a tool. If you don't practice how to use this tool, then you're not going to know how to do it when it comes time to a test, and then and you'll have to know how to do it. So that's something that you might want to spend time on. So if you wish, use Excel to do some of the problems on the homework. Some of the homework ones are going to ask you to add a lot of numbers together. They'll get ugly. It's part of the game, folks. It's part of what you got to do. All right? Now, note the cumulative functionality in Excel only counts down. All right? So what happens if I ask you to calculate
more?
Just start at the top and then
Well, let's figure it out. Probability of flipping 20 or more heads on 25 flips. So technically what you would need to do is you would have to figure out what's the probability that x equals 20 plus the probability that x equals 21 plus the probability that x equals 22 plus the probability that x equals 23 plus the probability that x equals 24 plus the probability that x equals 25. Okay? In theory, that's what you have to do.
What if we count tails instead?
You can count tails, yes, although I'm gonna get to it the same way, if you don't mind. You'll see it when you see it. Alright? So the key to this, folks, is realizing that what happens if I add all of the probabilities up? What do you get? 1. Right? So remember that the probability of this plus the probability that x equals 0 plus the probability that x equals 1 plus probability that x equals 19, if you add all of that up, you get 1, right? And note, this, what is this doing?
Coming out of Excel.
It's counting down, which is what Excel does, okay? So if you want to find out what these numbers are up here, 20, 21, 22, 23, 24, and 25 added together, all you have to do is take 1 minus this to get it, right? That's the key. That's one of those probability sums that you should always be able to throw around as needed. The sum of everything has to add up to 1 always. Always. So, the probability, oops, I'm blue, that x is greater than or equal to 20, which is our 20, 21, 22, 23, 24, and 25, is the same as 1 minus the probability that x is less than or equal to 19. And this is counting down. And do this in Excel. And that is a very common practice in statistics and in probability that you often work with one side only, and if you need to get the other side, you always utilize the 1 minus capacity of probability to do that, okay? So if you're ever trying to do more than, remember that it is always 1 minus less than. And this is what makes this doable using Excel, even though it always goes down and never goes up. All right? Does that make sense? It's one of those where it makes sense, but it's one of those where you're like, well, I won't know how to use it until I have to, and that's kind of the way it works to some degree. So, let's try one of these out of the book then in 5.2. What did I assign in 5.2? I will just do an odd one, that'll be safe. Alright, so yeah, every 4 after that. Alright, so. Alright, so let's do number 20. Or is that one of them that I assigned? 22? Alright, let's do number 20. I ask, oh, the numbers are too small for that. Aren't they? Okay, so let's do 21. A doctor's office has a no-show probability of 0.1. In other words, 10% of the time, people don't show up to his doctor's visits, right? Which probably isn't that far from the truth. If the doctor has 18 appointments a day, what is the probability A less, therefore do not show? Alright, so how would you answer this question? What are we trying to find? What numbers are less than 4? Alright, so we want to do the probability that x equals 0 plus the probability that x equals 1 plus the probability that x equals 2 plus the probability that x equals 3. So what's the probability that he has 0 no-shows? How would you use that hit or miss binomial probability? Combination of 18 things taken 0 at a time. What's my p?
1 in 10.
0.1. What do I raise 0.1 to? 0th power. What am I going to multiply it by?
9 tenths raised to the 18.
1 minus 0.1, and technically you guys can do that, 0.9, do that in your heads. And that's going to be to the 18th power, right? That's a quick calculation. And then you're going to add to it. Do the next one. 18, choose 1. Raise 0.1 to the 1st power. Raise 1 minus 0.1, which you're more than welcome to call that 0.9 right off the bat, to the 17th power. Right, that's the probability that you get 1 no-show. Step again. Plus the combination of 18 things taken 2 at a time, times 0.1 raised to the 2 power, times 1 minus 0.1 to the 16th power. And again, this is going to form a pattern, so the pattern should be relatively easy to follow as you keep going, right? One more, plus the combination of 18 things taken 3 at a time, times 0.1 And again, all that stuff is doable. Again, since this is a counting down example, you'd be more than welcome to calculate this in Excel as equally as well as cranking the numbers out on your calculator. Either way you wanted to do it. So those are the probabilities that you have to add together if you punch them and grind them out on your calculators. Not pleasant numbers. But you can do it. Again, this is the sort of thing that if you wanted to do it by hand, and this is what I had to do when I did it, right? Is I'd have to get out, you know, my professor when I did this, he said you must round things to at least 6 digits every time. That's what he told us. I was like, fine. I rounded things to 6 digits according to his rules, whatever. Me, don't round anything, just use it all. Right? Use the memories on your calculator to add stuff together as you go. And again, the difference between using this and using Excel use your binomial distribution. I want 3 successes, 18 trials. Success happens 0.1, and I want cumulative true. Done. So those are the sorts of things that you want to be careful with, right? So what did you guys get when you added those all up?
0.91803159018.
03159, which we would say is approximately 90.18% of the time. And again, note Excel gave us the exact same number with 4 clicks of the button.
I did that. Proud of myself.
Good work.
Thank you. I tried to make this kind of cool.
So again, this is the idea. And I am okay with you guys doing this in Excel and just writing the answer down. There's nothing wrong with it. Right? The only thing I can do though is that if you miss it, then all I can do is mark it wrong and say oops and go from there. Okay? Obviously I can't help you on that. You can try and print out what you did and I can try and grade it for you, but it's kind of up to you as to how much detail you want to give me. Now, how would we do the second piece of this problem, right? So the second piece of this is at least 2 patients do not show. What does at least 2 mean?
Not 0 or 1.
Not 0 or 1. So what are all the numbers that this applies to?
A lot.
X equals 2, plus the probability that X equals 3, plus the probability that X equals 4, plus dot, 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 plus the probability that X equals 18. Right? you should be going, hell no.
That's why I did drop this. Gotta stop that.
So this is where you use those probabilities, rules of probability, that everything adds up to 1, right? This is also equal to 1 minus the probability that x equals 0 plus the probability that x equals 1. And that's why you use this sort of a concept to simplify your problem. Because you don't want to have to calculate 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and 18. That would suck. Okay? And the cool part about it, folks, is that we've already calculated x equals 0 and x equals 1. We did it in the last problem right up here. So we can already answer this one in one fell swoop, right? Again, this is why sometimes it's relatively nice to do it the long way, because when you have to do some shortcuts or some extra problems, there's a good chance you've already calculated some of the probabilities, and you can kind of snap your fingers and get the answer. So if you do 1 minus the sum of those two guys, what did you wind up getting?
54.97%.
Which is sort of kind of bad for a doctor's office if you think about it, right? This probability gets at least 2 no-shows. It's better than 50%. That sucks. I wouldn't want to be a doctor if that were the case. All right, so anyways, this is just to give you an idea of the sorts of problems you're going to have to deal with when it comes to Chapter 5 stuff.
What do you do for the percentage for the last one is 100% then, right? And it's been all show?
That everyone shows?
Yeah, it's the last one on that
No, it's not everyone. So C is, what is probability of 0 no-shows? If everybody shows up, that means that you have nobody not showing, right? So what's the probability that x equals 0? It's right there. We've already done 0.
So that's
It's just 15%, basically. Whatever that number was. 4675. Again, if I were a doctor and that was the case, I would be pissed.
That also means there's an 85% chance you can double book.
True, which is of course exactly what they do. That's why you have oftentimes 2 or 3 patients waiting at the same time, because they assume 10% of you are not going to show up anyways. It's also why airlines overbook seats too. They have a percentage for number of people that aren't going to show, and so they'll overbook, assuming that there's going to be 3 or 4 or 5 people that don't show for every flight. And therefore, it's perfectly fine if you oversell it. Unfortunately, if then you have to ask a patron to exit the airplane, you call the police and you drag them out and bash their head against the wall and get sued for hundreds of millions of dollars.
And they go to the doctor.
Yeah, and they probably will show. All right. So, anyways, there's 5.2, folks. 5.3 and 5.4 are similar, except they are slightly different distributions, but they are on the same lines as what we were doing right here. So they will be calculations that you can crank out doing long ways and short ways, Excel ways, or shortcut techniques. And I will try and show you as many of those as possible on Wednesday. All righty?